So I got a bit confused at the end of filming that last section on the positron emission of the carbon. So, right, because a positron is the antiparticle of an electron, it's an anti-beta emission, if you want to think of it like that, okay? So instead of the proton number going up and the mass number staying the same, the atomic number goes down one and the mass number stays the same. We're getting a proton converting into a neutron, actually, inside it, with the emission of the positron. Bit of a weird situation going on there. Okay, on to part 6. What is the decay constant of carbon 11? Decay constant lambda is ln of 2 over t half. So we know t half from the article is, I think it's 22 minutes, was it? 20 minutes. So it's 1,200 seconds. Okay, so then to get the decay constant, it's ln of 2 divided by 1,002. Oh, sure. So it is 5 point. Sorry, I should write it fully. Lambda is ln of 2 over 1,200 seconds, which gives me 5.776 by 10 to the negative 4 decay constant per second. It's things per second, emissions per second, essentially. Okay, explain why the carbon 11 nuclei using the PET scanner must be produced in a cyclotron in or close to the same hospital as the scanner. PET scanner. Because of that short, because of the short half-life. The C11 must be used quickly. You can't go transporting it around the place, really, because it'll just all decay on you. Okay. Part 8. Give an expression for the momentum of the particle in the cyclotron in terms of the magnetic flux density of the field, the charge on the particle, and the radius. Okay, so we know that the force, because of the cyclotron, is due to magnetic fields, and that's Q, V, B. Okay, I have my Q and my B. Cyclotrons go around in circles, so I also know that F is equal to what's F? mv squared r. All right. No, sorry, mv squared over r. Okay. So I want mass times velocity, and I want it in terms of B, Q, and R. So I need to mix, so these forces are the same thing, okay? What I do want is, I need the R. So let's, and I don't really want V squared. Let's leave the V in there. Okay, what I can do is I can say here that mass is force times R divided by V squared. Okay. Yeah, grand. So I also know that, no, I don't think I want to do that, do I? Okay, over here I know that velocity is the force divided by QB. Yeah, that's grand. So I want mass times this. Mass times this. So the momentum mv is mass times F QB times V. Okay, but I don't want that M in there because I want I want QB. I don't want the F or the M. So what I want is the OR, do I? So mass times velocity. So velocity is F divided by QB, grand. And then I know that mass is F times OR divided by V squared, grand. So if I multiply this, I know what to do. I multiply this by velocity, okay? This is QVB. Aha! Bring that down there. So I've got my force due to the magnetic field is, the centripetal force is this, mv squared over r. I can rewrite it in terms of m is equal to f r over v squared. But I know that the f is qvb, right? And that's times an r divided by a v squared. One of those v's divides into that, and I have qb and r. I'm very nearly there. And then this is mass, but momentum is mass times velocity. Okay, here's my mass, so that's q b r divided by v, that's my mass, times my velocity. Get rid of that. Momentum, there we go, is q b r. And the marking scheme says it's q or b, that's the same thing. Lovely.